Thank you. Yeah, maybe we should start the clock. So thank you for the invitation. I'm very happy to be here. It seems like really, really a great event, and thank you for the organizers. And today I want to convey a very exciting line of research based on the MPC in the head. And I remember the first time I sort of looked into the papers and understood these ideas, and it was like, for me, it was a blow-minding. Wow, that's like amazing. So I hope to share this excitement with you as well. And I will sort of start with the basics. So the first talk will be about zero knowledge. And thanks to Manoj. Where is Manoj? Thank you. Zero knowledge needs no introduction, but I'll just give you a brief overview of how I capture zero knowledge proofs. So basically, when we talk about a proof system, we consider a mechanism where we can prove the validity of mathematical statements or true assertions, where false statements should not be convincingly proven, or a verifier that sort of interacts with the prover should not be able to be convinced that this statement is correct. And we also want the statement to be easily verified. And easily is not well defined still, but you can think of the computational task of the verification should be simpler or easier than proving the prover's task. And on top of that, we want to also add another layer of privacy for the prover. So the prover has some secret input. We call it the witness. And zero knowledge essentially ensures that the verifier will not conclude any information on this secret data. And this is a great object with many, many important applications. One important application is in the context of MPC, which I'll say more also in the next talk, where we use zero knowledge to sort of compile weaker protocols into stronger security by ensuring that the parties behaved correctly. We can also use zero knowledge to build post-quantum or, in general, digital signatures, which we'll also discuss a little bit later. In the context of this workshop, zero knowledge were used to design private blockchain, as was explained in the previous two talks. Basically, the details of the transaction could be encrypted or hidden under some cryptographic private object. And zero knowledge ensures that the users behave correctly, meaning no double spending and so on. So, and there are quite many other applications. So definitely, this is like a very, very important object and well worth studying. Great. So this talk is about, indeed, zero knowledge, but based on MPC in the head technique. So I just want to give you a brief introduction to MPC, secure multi-party computation. So the setup is that we have a set of parties, and they would like to communicate and compute some function on their private inputs. Where the goal is to learn or extract the output of the function and nothing more than that. And so this is the privacy requirement. We also want to ensure that the computation was performed correctly, so that the correct output for some definition of correctness was computed by the protocol. So this is a very, I would say, active research line in cryptography. And we have different models or different settings that we consider. Just for the purpose of this talk, let me distinguish between what we call semi-honest and malicious, or passive and active attacks. In the semi-honest, we prove security in the presence of a weaker, benign adversary that we assume to follow the protocol's instructions. And the goal of this adversary is to, you can think of it, violating the privacy of the uncorrupted parties. So basically, he would like to, or that adversary would like to examine the messages it receives from the uncorrupted parties with the goal to extract more information about their secret inputs. Malicious or active adversary is a stronger adversary. Basically, we do not assume anything about the strategy of this adversary. It could attack the protocol in an arbitrary way. It could try to violate the correctness. It could choose its own input based on the inputs of the honest parties, and so on. So, so these are the two distinctions with respect to the attack model. We also have two main distinctions with respect to the number of parties an adversary may corrupt or take over. And this is honest and dishonest majority settings. Starting with the honest majority, up to strictly less than half of the parties may be corrupted or under control of a party, of an adversary. While in dishonest majority setting, all but one of the parties may be corrupted. So this is a much stronger setting. Okay, so one more building block, which I'm going to refer to during the talk, is oblivious transfer, or OT. And here we have, it's a two-party functionality, where a sender has two inputs, or perhaps I can say the most basic variant of OT is 1 out of 2 OT, where the sender has two inputs, could be bits or strings, and the receiver has a bit, and the goal is for the receiver to learn S sub B without learning anything about the other input, while the sender should not learn anything about the input bit of the receiver. And this is like a very fundamental primitive in secure computation. Basically, if you can compute OT securely, you can compute any function, any efficient function securely. And since it's a very fundamental object, it has been studied quite a lot. We have pretty efficient implementations, concretely efficient implementations of OT. We have OT extension, which I'm not going to discuss. But at this point, OT has a lot of sort of the concrete efficiency of the protocols we design today goes back a lot to the efficiency of the OTs, because these protocols use many OTs. Okay, so enough about, oh, what did I do? Okay, enough about OT. Let's start with proofs. And when we try to understand or study proofs, we have different aspects, qualitative aspects that measure the quality of the proof, basically. For a start, we can ask whether the proof is for the class P or the NP, the class NP, where in NP we have this additional private input for the prover that is called the witness. The proof could be interactive or non-interactive. Where non-interactive proof means that the prover sends a single message to the verifier. When we talk about non-interactive proofs, we can think of two, we'll say, modelings or variants. One is a kind of that requires a trusted setup. It was mentioned before, and this is the kind that is embedded in the Zcash systems, blockchain systems. Or it could not rely on any trusted setup. And in this case, we call these proofs transparent. And you'll see, I'll explain why. We could also require that the proof is sound in the sense that the prover cannot cheat, or we can also require zero knowledge, meaning that the privacy of the provers is maintained. Succinctness. For the sake of this talk, I will require or define succinctness as a sublinear communication complexity, meaning that if you think of, if we have, let's say, if we have an NP statement, we have a verification algorithm, and you can think of this verification algorithm as described by a circuit, a Boolean or an arithmetic circuit. This is a computational model we are usually working in. And I would like the size of the proof to be sublinear in the size required to describe this circuit. And different types of proofs shows different trade-offs. We can show very succinct proofs, just a matter of just a few kilobytes, and more than that, as you'll see next. And finally, we also care about the type of assumptions we need to design the zero-knowledge proofs. So basically, we distinguish two categories, either public key assumptions or symmetric key-based assumptions. And why do we care? First of all, due to efficiency. So public key assumptions are known to be orders of magnitude slower than symmetric key crypto. And also because it was also mentioned in the last of the previous talk, if we care about post-quantum crypto, then we should have, or we should focus on the symmetric key based assumptions, because all the public key crypto we have today are sort of the algebraic structure of these constructions are susceptible to or sort of are breakable by quantum-based attacks or algorithms. Good. So this is the taxonomy. Now we can also distinct based on the combinatorial mechanism that underlines these proofs. And also Manoj mentioned a little bit. So this is a very crude sort of split of the abstractions we can consider today, since this area is so active. By now, each path took on its own life. And there are many, many papers being published all the time. So might be that unintentionally I even missed a paper or two. But let me try to explain what are the mechanisms, combinatorial mechanisms used in today's zero-knowledge proofs. So the first one is a PCP-based zero-knowledge, which means that very roughly the prover sort of makes or prepares a very long proof, which he commits. You can think of it as an oracle. And the verifier probes this proof, and for some limited amount of queries, it should be convinced that the proof or the statement is correct. And the properties of this kind of proofs is that no setup is required. On the other hand, the prover's complexity is relatively high, because generating these PCP proofs is a very complicated computational task. But by now, this abstraction is extended to what we call IOPs. And I mean, the way I described the PCP mechanism is in a non-interactive way, but you can actually extend it to support interaction as well. So that was the first category. The second category is an extension, or you can maybe even think of it as a simpler mechanism of PCPs called linear PCPs, where there the verifier's queries are not just probing, but actually some linear functions. And this category mechanism is actually the one that underlines the SNARK basic protocols, and specifically the one that is used in Zcash. So here, the disadvantages of this kind of proof systems is that the proofs are relatively short, or very, very short, not relatively, the shortest you can actually achieve. And the verification is very fast, even sublinear. On the other hand, the constructions rely heavily on public key crypto, which means that they are not or could not be quantum secure. And also, these constructions require a trusted setup. For instance, a common random string or reference string. Finally, we have the line of works that is based on interactive proofs, originally initiated by the seminal work by Goldratt, and Rangan. And here, these proofs also do not require an trusted setup. Well, up until recently, like the most recent work, they also relied on public key assumptions. Some types of commitment schemes. The most recent work shows how to actually remove or reduce the assumption into a symmetric key crypto. Relying on public key so far had the disadvantage that I mentioned before. It's not quantum secure, and it wasn't very efficient for the prover side. Okay, great. So today I'm here to tell you about the fourth category, which is based on the MPC or multiparty computation. And I will not compare yet these constructions. I'll do it after I'll show you some of the constructions. So this line of research is, I don't know, but this is fair to say that this is like the first paper that actually started this. And this zero knowledge from MPC, showing how to construct zero knowledge from an MPC protocol. Okay, so what is our goal? We have an NP relation, and we would like to construct zero knowledge proof. In order to use, right, we have MPC, we have protocols. So we need to define a functionality to be used by our protocols. So here's the functionality. We take the witness and we split it in a secret shared format, where each input, each share, is given as an input to each party. And basically, what would the functionality do? It will combine the shares of the witness, and then it will invoke the algorithm that verifies the correctness of this NP statement. And let me show you how to use off-the-shelf protocols. And this approach works both by using honest majority, MPC, or OT-based. And let's assume that our starting point is a very simple protocol. We start with a semi-honest protocol, let's say 5 parties and 2 corruptions. Another requirement is that the protocol is perfectly correct, okay? Meaning that the output of the protocol is always the right one. Good. So here's the fantastic idea of building zero knowledge from MPC. This is the setup. We have a prover and a verifier. And as a starting point, the prover is going to generate those shares I mentioned before. And it's going to emulate in its head, in its mind, the protocol execution on these inputs, right? So this is the execution. And a protocol execution employs or generates views for the party. So a view of a party, its initial input, the randomness was used for the execution, and the incoming messages. Right. So here is the first step in the zero knowledge protocol. The prover takes these views and commit to them. sends a commitment to the verifier. Remember, a commitment is sort of, think of it as an envelope that seals the messages inside. The verifier probes now these commitments, meaning it will choose a pair of parties or pair of views. And now the prover will open these views. What would the verifier check? It would verify, first of all, whether the output of the parties is 1. Remember, if the statement is valid, then the verification circuit would output accept. Otherwise, it needs to output reject. So that's the first one. Wait. Okay, sorry. The second thing the verifier needs to check is whether these two views are consistent. What does it mean? It means that the incoming messages from one view are consistent with the outgoing messages of the other view and vice versa. Okay? Now let's understand why is it a zero-knowledge proof. So completeness follows immediately from the perfect correctness of the protocol. If the protocol is always correct, that means that the parties will always output 1, because the verification will always output 1. And also, the views will always be pairwise consistent, because the prover is not cheating. What was your knowledge? So my requirement from the protocol was that it is resilient against 2 corruptions. What does it mean? It means that an adversary that corrupts 2 parties can be what, like in our language, simulated. So basically, to prove that this protocol is zero knowledge, we could actually directly rely on the privacy property of the semi-honest protocol. Meaning, you can think of the verifier as an adversary that observes 2 views of the protocol, and then cannot learn anything about the honest party's inputs. So essentially, zero knowledge is immediately implied by the privacy of the protocol. Great. Proven soundness is a little bit trickier, but not much more. So let's assume there isn't any valid witness for this statement. So what does it mean? It means that there isn't any global execution that is consistent, right? Because either the verifier or the parties, one of the party will output 0, right? Or there must be at least one pair of views which is inconsistent. Okay, more details. Since the protocol has perfect correctness, okay, it must be the case that at least one of the parties or subset of the parties output 0, and then the verifier rejects when it checks that. Or the global consistency implies global inconsistency implies a pairwise inconsistency where at least a pair of views is inconsistent, right? And the probability that the verifiers reject is n choose 2, right? What's the probability to hit this pair of inconsistent views? Good. And not only that this is a zero knowledge proof, it's also maintains a stronger property that Manoj mentioned. It is a proof of knowledge. You can rewind, right? You can rewind and open different views, and then you can extract the witness. Okay. So now we care about the communication complexity or the proof size. The way I use the MPC protocol is just the most simple way I could have. So basically, the size of whatever, the size of the messages communicated by the prover relied on the communication complexity of the underlying MPC, meaning that the randomness complexity used by the parties, right, and the input size and their views, the incoming messages. So the efficiency of a zero-knowledge proof in this paradigm directly relies on the efficiency of the underlying MPC and the size or the sizes of the views embedded by the parties. And this paradigm is very flexible, and the fact that we can embed different MPC protocols implies that we have many extensions for this basic protocol. Let me mention some of them. For instance, the way I just explained it, I explained by consistent views, right? And for that, I need two corruptions, or security in the presence of two corruptions. We can extend this view, to only consider a single corruption. So then how do we prove, or how do we check consistency? In this case, we can commit to also both the views and the communication channels pairwise between every pair of parties. Now, when we want to test consistency, we will ask to open a view and all the communication channels between every other party. And then we can check consistency between all these. So that's one thing. Another thing is that right now I require perfect correctness. We can relax this requirement to statistical correctness, and then use a coin tossing mechanism to ensure that the prover cannot cheat, right? If the prover chooses the randomness of all the parties, it might come up with the bad randomness. Even this is all statistical error. So if we use a coin tossing in some sophisticated way, then we can ensure that the prover cannot cheat. And using also stronger MPC protocols, which I'll show you next, that sort of secure in the presence of the stronger active adversary, we can even achieve better soundness. Okay, and maybe the last extension here, we can also work with dishonest majority protocols. So as I mentioned, dishonest majority protocols work in the OT hybrid. What does it mean? I mean, we can abstract these protocols by sort of describing them in a model where the parties have oracles to the OT functionality, which I mentioned before. And in this scenario, we could actually use verify the correctness of these OT oracles in the proof as well by only committing to the input and output from the oracle. We don't need to commit to the entire communication by these OT oracles. And you can actually extend this to more complicated oracles, not just OTs. Okay. So we can, I mean, the fact that this paradigm is very flexible, we can actually instantiate it with many different MPC protocols. And some of the follow-up works used protocols like GMW. So you can actually use 2,5 or 1,3 protocol where you have, let's say, 3 parties and a single corruption. So you could just take off-the-shelf classic protocols like GMW and BGW. This is for the MPC people. These protocols or these instantiations could actually be made practical and has been implemented and relies only on symmetric key crypto, which means that this is potentially could be post-quantum secure. So there are different instantiations, and I want to focus on one of them. So this paper by Giacomelli, Matson, and Orlandi was basically the first paper that demonstrated that this method of MPC in the head is actually practical. So what did they do? They instantiated this protocol with a GMW, a 3-party protocol based on GMW in the OT hybrid. So here the prover only sends 3 views, out of which we open 2 of them. So that was great. They actually implemented it. It was very fast. The downside of this approach is that the soundness is constant, right? Because we only open 2 views out of 3. So they had to repeat their construction, their protocol sufficiently many times to reduce the soundness to the -40, to the -90, it depends on the parameter. So that sort of, this inflates the size of the proof. So, so remember this table from before when I gave you the different categories of abstraction of zero-knowledge proofs. So far, or before the paper I'm going to show you, when ZKBoo was introduced and also based on the ICOS paper, all the constructions sort of achieved linear communication complexity. So the proof size was linear in the size of the circuit, the verification circuit. So you mean in the PCP approach? Right, so you can think of it as computing FFT on a polynomial where the degree of the polynomial is the size of the circuit, or close to the size of the circuit. Right, so now I want to show you our follow-up work. This is the Ligero proof system, and this is a joint work with Scott Ames, Yuval Ishai, and Mutu. And so at this point, when we started working on this very, very exciting research area, we kind of liked very much this MPC and the head approach, which basically you can take an honest majority protocol, you can translate it into a zero-knowledge proof in a very clever way, but simple to explain. And we were at the position where these have shown to be practical and implemented. But our goal was to reduce the communication size. We wanted to achieve a sublinear proof size. But how can we make it sublinear, right? We sort of had this, think of it as a stop sign, right? I just told you, communication complexity depends on the sizes of the views employed by the protocol. Right. So that's a very good point. I mean, Yuval is saying you can use a protocol that sort of is using fully homomorphic encryption, and then the communication complexity is very small. It grows only with the input and the output size. But our goal was, or Yuval and the author's goal, was to use the MPC protocol in a black box way, meaning that we do not need to rely on the code of the algorithms that generate the messages in the MPC protocol. And this black box approach that sort of follows the entire line of this MPC in the head introduces much more practical protocols. Okay, so good point. And here is a key insight in improving, or in the direction of improving these previous constructions. Let's try to work with protocols where the communication per party is small, is not proportional or grows with the circuit size, but is sublinear. And we have such protocols in the literature, like Ishai, the IPS09, and maybe here, if we actually try to use such a protocol, then when we open the views, then we need to send less information. And indeed, this is the base, the key insight that underlines the Ligero proof system, where the main contribution of the paper lies in translating an MPC protocol into what we call interactive PCP. So it's a PCP-based protocol where the prover and the verifier further interact. And so transforming this IPCP into zero knowledge is based on, like, I wouldn't say standard, but techniques that already appeared in the literature. So this is the main contribution. Let me show you how do we do it. But before that, let me state the main results. So we basically introduced the first sublinear zero-knowledge argument that does not require any trusted setup. It's simple. It was implemented. Only required hash function for the Merkle commitment. Potentially, it could be post-quantum secure. I'm saying potentially because we haven't proved it. This is like a good follow-up question to prove that these proof systems are post-quantum secure. And like the bottom line is that this is the first sublinear zero-knowledge argument for any NP statements that does not rely on any of the complex PCP machinery or public key crypto. And the complexity or symptotic complexity of this proof system is square root the size of the circuit, the verification circuit. This proof supports both Boolean and arithmetic circuits. It can be made non-interactive via the Fiat-Shamir transform, and this is what I call transparent. And that means that the messages from the verifier are basically just random strings. And the prover's complexity is basically building a Merkle tree for square root number of leaves, where each leaf is of size square root also. And this sort of, and this boils down to asymptotic complexity for the prover of square root C times square root evaluations of FFTs. Okay, so these numbers are outdated. It doesn't matter, I mean, the precise numbers, because since then, like it was 3 years ago, we have plenty of optimizations embedded across all proof systems. But just in essence, I want you to understand the big picture. So the Ligero proof system somewhat lies between the linear PCP or Zcash-based constructions and the ZKBoo, the one that I showed you before, right? Basically in all the parameters. So communication, we definitely cannot compete with the linear PCP, where there the proofs are like just bytes. But we can get better proof lengths than the ZKBoo, because their technique, their approach is linear in the size of the circuit. In terms of prover's time, remember the linear PCP-based approaches has like really worse prover's complexity. So we somewhat lie in the middle, both in prover's time, verification time. And I just want to mention an interesting feature that we have. So our verification time is also linear, but for in the case we want to amortize the computation, let's say we want to prove many statements, or even by taking advantage of the internal structure of the circuit, we can actually go much below that. So that's an interesting feature in Ligero, and of course, like ZKBoo, we don't need any trusted setup. Yeah, it will be sublinear. So I can mention it later, but basically you can get rid of one of the tests. One of the tests that we do in the proof. Okay, so the Ligero proof system has 5 rounds, And let's try to understand in more details. So for the sake of this talk, let's assume we have a Boolean circuit that computes the verification algorithm. And let's color the wires values. So take these wires, take these values, and arrange them in a matrix. And this matrix has the parameters of A and B, which will sort of dictate the complexity of the proof system, both for the prover and for the communication complexity. And we sort of arrange them by repeating these values. The method for Boolean arithmetic is slightly different, but the number of repetitions is very small, only twice for Boolean, 3 times for arithmetic. So you sort of, you fix A and B in an optimal sense to get good parameters, and this is where we get the square root. Okay, so what would the prover do? After arranging this matrix, it would encode each row in this matrix using some error-correcting codes. And the overhead in practice of the encoding is usually between 4 to 6x. And here is the proof system, high level. The prover first commit to this matrix. So each column, you can think of each column as a leaf in this Merkle tree. And it would send the roots of this commitment to the verifier. Next, the verifier will send what we call multipliers, or first challenge, where the verifier will compute, the prover will compute the linear combination of every row in this matrix. And we'll send the linear combination. And next, the verifier will probe this matrix, and it will get back these columns, corresponding columns from the matrix, which it will check consistency with what you received in the previous message. This is very high level. I'm omitting many details, but just want to highlight the parameters of the proof system. So the proof length, right, is sending one line, right? And then also opening, it would be order of kappa, which is kappa is the security parameter of columns. And this is, you can think of it as something similar to what we do in cut and choose based techniques when we repeat a process or a computation many times and then check a subset. So this is the size of the proof size, and the prover basically computes order of A FFTs of size Bs. This is the complexity of the prover. All right, so yes? Oh, okay. So these are the what I call the multipliers. You use them to compute the random linear combination of the rows in the matrix. You take F1 times the first row plus F2 times the second row plus. Does this make sense? Okay, good. So I promised our MPC in the head. Where's the MPC? A different view of what's going on the prover side. So you can think of these columns as a view of the parties or servers in MPC protocols, where the prover takes its own input, the statement and the witness. It could secret share them and send to each server or each party those secret shares. And each column corresponds to a bunch of set of secret shares. Think of Shamir secret sharing, if you know. I'll explain that in a second. And basically, the input of the prover will not be just the statement and the witness. you can consider it as an extended witness, meaning, like I mentioned it before, all the intermediate values that go through the circuit, the verification circuit. So we have order of size C values, and we can break them into blocks, and we can secret share each block separately. So that is the first part of this MPC protocol. And now we basically want to verify the correctness of this secret sharing. So it's a very simple MPC. No need to sort of compute anything, only verify the values secret shared by the prover. Okay, so this is these are the tests which I haven't explained yet, and so it's the sort of the type of computation you want to verify. It's what we call a degree 2 computation, and there aren't any communication exchange between these two parties. So this is a very, very simplified MPC protocol. The input of the prover, right? So you can think of the input of the prover as the statement, and the extended witness, which is basically all the intermediate values go through the circuit. Okay, so a little bit more technical. So the first tool we're using, or maybe an extension of this tool, is the Shamir secret sharing. So how does it work? It's a very, very famous and fundamental tool used also in MPC and many other areas. So basically, in a secret sharing, we have, you can think of a dealer who has a secret, and you would like to share its secret among a set of n parties, such that only if t plus 1 of the, or t of the parties collude, they can reconstruct the secret. And this construction is based on polynomials. So basically, you define a polynomial where the free coefficient of this polynomial is the secret. And then you evaluate this, and the rest are random, and you evaluate this polynomial on some fixed set of inputs, 1 through n. And you sort of, and the shares of this, of the outcome of this computation, these are the shares, the values that are computed based P of 1, P of 2, and so on. Now we can extend this, this tool to what we call packed secret sharing, where instead of sharing a single value, you can share a block, okay? And this tool has a lot of implications on obtaining the efficiency I mentioned before per party for MPC, right? Remember, we wanted to use MPC where the actual amount per party is small, could be even constant. And the way you actually do it is by using packed secret sharing, because then the actual, the amount of work amortizes per party. Okay, so we have several tests. Let me explain 2 of them. So the first test is where we want to make sure that these Shamir or Reed-Solomon encodings were done correctly. So remember, this is the starting point. And the verifier sends what I call the multipliers. And now the prover sends the linear combination of all these rows. And you can think of each row as a polynomial. So now, when we open a bunch of columns, what would the verifier check? First, it will check that the degree of this linearly combined polynomial is of the right degree, right? In this case, it should be t plus L, where L is the size of the block we are committing to. Second, you would need to check the consistency between this Z polynomial with the committed columns, right? So this is essentially what the verifier recomputes the evaluations of this polynomial on the points it was probing. And this basically, in the literature of MPC, you can also think of it as what we call VSS, or verifiable secret sharing, where we want to verify that the secret shares were done correctly. And actually, the analysis of this protocol or this test wasn't as simple because the prover might corrupt the parties in this MPC and the head protocol after observing the challenges coming from the verifier. So this is what we call adaptive security, meaning that after seeing the messages, the adversary may decide which parties to corrupt. So that means that the analysis, the security analysis, was more complicated than what might seem exactly, because you want concrete efficiency. So it was quite challenging to analyze this setting. Thanks. So that was the first test we're using. Let me explain another one. And this is for testing quadratic constraints. So this is what I called before a degree 2 computation. So remember, if we have multiplication gates in our circuit, we want to test whether they were sort of computed correctly. So that means that you can think of it in terms of the matrix computation, that we have rows where we want to test the product-wise computation. So maybe saying it differently, we align the values in the matrix in a way that allows us testing it blockwise. Okay, so you do it in a more sophisticated, you align the values in a more sophisticated way so that you can actually test it blockwise. And here, basically, in terms of polynomials, what you want to test, you want to test that the product of two polynomials sums up to a third one. Because if we have two lines and their cross product equals the third one, so in terms of polynomials, means that the values component-wise in the actual locations are multiplied accordingly. That's basically what you want to test. And again, we receive from the prover, or the verifier receives from the prover, this what we call the product. So basically, the prover will compute the product of these polynomials, subtracting the result, right? And it will take the linear combination of all these sort of computations we want to check as before. And then the verifier is probing kappa places, kappa positions in this matrix. And here we have two things we want to test, very similarly to the previous one. First, we want to test that the polynomial was computed correctly, okay? This is sort of a generalization. In Ligero, we basically want to test that this polynomial equals 0, because we take one value, multiply it by another, and then subtract the actual result. So it will boils down to 0. So this is first what you want to check. And And the other thing is that you want to check consistency with the matrix. Okay? So as before, you want to test that the polynomial was computed correctly and that the outcome of the polynomial in the probed points, let's say for now it's 0. Okay? So that was the second test. I don't have much time. So, Arpita, you asked a question. We have another test, which is what we call a linear test or permutation test. And basically, what you want to do is that when you align the values in the matrix, you want to make sure that you maintain the consistency between the rows, because an output from one gate should sort of be consistent with the input to the next layer. So this is an additional test which I am not explaining now, but maybe we can take it offline. I'll explain more. Okay, so I'll just take 2 more minutes. So the Fiat transform heuristic, this is what Manoj mentioned. This is a way to transform a transparent zero-knowledge proof where the messages are basically random strings. So the prover can sort of generate them using a random worker or a hash function in practice, and then sort of compute the entire messages of the protocol. And it has been analyzed and still analyzed, and it raises a lot of interest by the community, understanding the actual security of, also from theoretical point of view, of Fiat-Shamir. And it has a lot of impact in practice, definitely. That's how you collapse the rounds in this proof. So that was one point. I just want to say, how can you use this zero knowledge to actually construct signature schemes, and specifically post-quantum signature schemes from zero knowledge? And this is amazing because this is a general way to do it, and it turns out to be very, very efficient, very practical. So basically, you choose a PRF key, right? And you publish a PRF of some constant value, let's say 0. And the signature is a proof where you basically prove that you know PRF key that gives you this value, where the challenge of the proof is computed based on the message you want to sign on. Okay, so in Fiat-Shamir, this is a hashing of the first message of the protocol and the actual message you want to be signed. And this approach has turned to be, first of all, you can actually extend it to ring signatures, group signatures, and one of the candidates in the NIZK competition based for post-quantum signatures is actually based on MPC in the head. And it's quite competitive. So you can actually see how competitive these generic approaches to construct also signature schemes, which is quite surprising and nice. And last slide, I just want to say a few words about another paper that was joined with Yuval and Mutu that sort of pushes the limits also of these zero-knowledge proofs and shows how to use them to prove some properties or certify inputs to functionalities. For instance, in a setting like when we want to compute some mechanism based on neural networks. And there it's very important that the inputs are chosen according to some distribution or for some domain. Otherwise, the correctness of the mechanism could be sort of destroyed, basically, very easily. So, so this is an extension of zero knowledge where you actually can build a primitive called certified OT. This is, goes back to another paper, but also by Yuval and Manoj, that shows how to, they show how to use this, how to construct certified OT based on MPC in the head. In this paper, we make it, we sort of decouple the crypto part from the information theoretic part, and we have a more efficient instantiation of certified OT based on the tools I sort of mentioned before. So there are many directions you can actually take these tools. MPC in the head is a very flexible, is a very useful tool. And in next talk, I can actually show you how to build MPC from MPC in the head. So, thank you.